Good evening, everybody. Today we'll have a great talk by the authors of the Pyboost, or the other name is SketchBoost. This is fast gradient boosting algorithm, which is very suitable for multi-target tasks. So it can predict maybe even 1,000 targets simultaneously. And it is distinguished in that respect from the other boostings like XGBoost or CutBoost or LightGBM. So thank you very much, Anton and Leonid, that you agreed to make a talk. And please start.
Okay, thank you, Alex. Hello, everyone. Today I'm with my colleague Leonid. We want to talk a little bit about our paper from previous year NeoRIPS conference, which called SketchBoost, Fast Gradient Boosted Decision Tree for Multi-Output Problems. And first, I want to make a little bit introduction about what we were doing and why, to have some background. And I assume everyone knows what is gradient boosting with decision trees. For now, for the moment, it's a state-of-art algorithm for solve classification and regression tasks on tabular data. So, for example, if you can imagine the problem when you have a flattened table, that means any row of the table represents a single object. You have some labeling for these objects. You have no sequences, no spatial data. Probably gradient boosting is going to be the winner on this data set. Sometimes you can meet papers, for example, like a TabNet, FT transformers, and they claim that they outperforms the gradient boosting on the tabular data. Sometimes it's possible, but probably some of the results are maybe unstable and change from data set to data set, while gradient boosting is going to be quite stable algorithm. So if it's not going to be a champion on the particular data set, probably it's going to be very close to the top. So if it's impossible to use somehow the power of transfer learning, if you are learning from scratch, so the gradient boosting is a good choice for tabular data anyway. Also, it's actually very efficient for both train and inference. That's why it's going to be a winner not only on the Kaggle competition, but actually it's very popular in the industry. It's in such domains like e-commerce, banks, retail, and so on. And of course, all you know that boosting is a very cool toolkit. But today we will not speak about how good is it. We will speak a little bit about disadvantages of gradient boosting and how can we handle it. And the topic of our paper is scalability of the gradient boosting on so-called multi-output problems. So that problems, you wish your model output not a single number for a particular object, but like a vector of values. The most common example of such kind of problem is multi-class classification tasks. So in this task, you want your algorithm output the distribution of probabilities of each classes. A little bit less often, but also quite common, is like a multi-label classification. In that task, you want your model to solve a set of binary classification tasks with one model. So, for example, you have a single feature vector and multiple binary labels. So you don't want to grow like a zoo of binary classifiers. You just want to solve this task with a single model. And another example is like multi-output regression tasks. It could be very common, for example, in multivariate time series forecasting. You can imagine the task when you want to predict a multiple time series with just one model. Or you can think in another way. For example, if you want to predict a single time series, but for different time windows. For example, the first output is like a forecast for tomorrow, the second output like forecast the day after tomorrow, and so on. For example, if you speak about multi-label classification, it's a very common task in recommendation systems, especially in the finance domain, For example, if in e-commerce, probably it's not going to be very useful because you have like millions of items. In the finance, probably you're going to have up to 100 items, and you will not have like a very big actions history, you know, from users. So typically you will solve this problem like a multi-label when you have a client profile and you want to estimate the probability that he needs this particular product, like a credit or deposit or card or something else. So the products are limited. Sometimes you can meet this kind of task in industry. And here you can see the very popular gradient boosting toolkits, and some of them are able to solve all these tasks. But there are some actually some limitations. For example, all these frameworks are able to solve only multi-class classification tasks. If we speak about multi-label classification or multitask regression, only XGBoost and CatBoost are able to solve both. But there is a difference. Here, I should mention that this material, everything I will speak, to the time of our research is maybe 1 year. For now, situation's a little bit changed, and I actually will mention. And if we speak on the moment of our research, both XGBoost and CatBoost were able to solve, for example, multi-label tasks, but there was one difference. For example, CatBoost supports fair multi-output models. What does it mean? On each iteration, CatBoost can build a model, can build a decision tree, which outputs like a vector of response. That means that number of trees in CatBoost will not grow with the number of outputs, with the number of classes, for example. For XGBoost, it's a little bit different because they claim in the documentation on that time that yeah, they can solve a multi-label task, but there is just a wrapper inside that fits single decision trees for single outputs. So it's not actually a fair multi-output with a single tree, but just a one versus all wrapper just built inside the XGBoost. For now, the situation changed a little bit, and maybe a few months ago, they released 2.0 version, and in that release, they say they can do fair multi-output. But speaking about our research, I will speak about the previous time when they cannot. Now, actually, they support both regimes, so you can choose even if you want fair multi-output or one versus all. So there are the options. LightGBM, as far as I know, maybe the situation changed in close time, but on that moment, they supported only multi-class classification. Okay, so I told that at least 2 of these frameworks can solve the multi-label classification task or multitask regression. So what's the problem with this if they already can solve this? Okay, here the problem is listed. This is a very simple experiment where when we generated 2 million instances dataset, it has 100 features, and we generated this dataset multiple times. And the only thing we changed from time to time is the number of classes in the target variable. We varied from 5 till 500, and we estimate the training time that needs for all of these frameworks for extra 100 iterations. What does it mean, the time for extra 100? All the boosting models have some constant costs that they need for make quantization, for data transferring from GPU to CPU, for example. So these costs are constant and not vary from number of iterations. here we try to measure only time spent for iterations. So how experiment was done? We train 200 iterations, we train 100 iterations and measure the difference. And what we can see here, we can see that train time grows linearly with a number of classes. So it's not very good because if we want to train 100 output model, we need the same time that that we train 100 times a single output model. We don't like this situation. But let's speak about why does it happen. For XGBoost, the things looks quite obvious. As I said, inside it's just a wrapper that trains single output decision trees in loop. For CutBoost, as I said, they can train fair multi-output. So the number of trees, the actual number of trees is not growing. It's growing the number of classes. So why it still have some bad scalability? To understand this, we're gonna deep dive to the gradient boosting theory. And now I want to introduce my colleague Leonid and give him a speech for he to explain us the problem. So I will mute now.
Yeah, hello everyone. Let me share my part of the slides. 1 second. Yeah, maybe somebody can say whether you see my slides or not.
Yes, we see.
My mouse, yeah, everything works. All right, so thank you, Anton and Alexander, for introduction. So I'll talk a bit more about the theory which lies behind GBDT, gradient boosting decision trees, and also a bit later I'll maybe say a few words about SketchBoost or Pyboost and about our ideas we developed. So yeah, let's start with a simple slide with notation. So we have a data set, of course. We denote by X and Y's our input and output variables, just our features and responses. Of course, we assume that our samples, they were generated independently from a known distribution. We don't need to know this distribution, but anyways, we assume that it lies behind our data. And we assume that we are given a loss function. So a loss function which just measures the distance between y's, between true values and our predictions. And our goal, of course, as usual, is to minimize our loss function. So let's say if we have a model F, we want to minimize this sum. So we just plug into our loss function y case, which are just true values we want to predict. Into our model, we plug x case, which so this is just our predictions. And yeah, our goal is to find a model which minimizes this aggregation of loss for this data set. Okay, so a few words about gradient boosting. So it's not gradient boosting on decision trees. It's just a general idea about gradient boosting. So this is an algorithm which, in a sense, tries to combine weak learners into a single strong learner, and it does it iteratively and greedily. So the idea is the following. So we need to have a set of weak learners. Let's say we have a set of decision trees, and at each step we try to add a new weak learner to our ensemble. And to do this, we again, as usual, we compute derivatives with respect to our derivatives of our loss function. Here, let's say we computed first order and second order derivatives, so gradient and Hessian. And then we try to find in our class of weak learners a minimizer of let's say first or second order Taylor expansion of our loss function. So in a sense, we just do a step using gradient descent or Newton method. So gradient descent is when we don't use second order information, and Newton method is when we use second order information. And after this step, we just add minimizer to our ensemble, and yeah, beforehand we just need to multiply it by some constant just to control the size of steps we make. So we just multiply it by a learning rate. All right, so this was the general idea of gradient boosting. GBDTs, so gradient boosted decision trees, they are based on decision trees. So we just, as weak learners, we consider just simple decision trees. And again, so I assume that everybody knows what decision trees are. So we have different nodes, and for each node corresponds to a split, and split is based on some feature and threshold of a feature, and then each our sample falls down into one of the leaves, and at each leaf we have a prediction. So whether it might be just like a class or it might be just a regression response, so something like this. So we have it for each leaf. And namely, so what we actually do, so we, if we consider our feature space, and if we have a plot of our data set, so we just consider like different splits of our feature space, and after several splits we stop, and each subset corresponds to one of the leaves, and for each subset we have just one prediction. So in a sense we can write this model as a sum of responses multiplied by indicator function. So this is just indicator function which checks whether X belongs to leaf Rj. So only one summand of in this sum is going to be non-zero, and we will have just one value for each leaf. All right. So we know what decision trees are, and let's speak maybe in more detail how actually we can fit a decision tree in GBDT. So in a sense, we can divide this problem into two problems. So the first problem gonna be fitting a tree structure. So we need to find a tree which is in a sense an optimal one, a tree structure which is an optimal one. And the second problem is for a tree with a given structure, we want to find leaf values. That's it. So first we need to find tree structure, and then we need to find leaf values. So let's start with the second problem. So let's assume that we were given of a fixed tree structure, so we know what leaf values are. Then everything is simple in a sense that we can just minimize the loss we have, the target function we have with respect to leaf values, and so we will. So since we are doing gradient descent or Newton method, so it's can be solved analytically because we have just an equation. Our target function is just linear or quadratic, and optimal leaf values are the following. Here, there is one maybe remark I should make. So if we consider second order derivatives, and if we have like for second order, so cachons for every sample, and if they are full matrices without any sparsity, then to find optimal leaf values, we need to solve quadratic equation, which means that we need to invert our cachons, invert these second order derivatives. Of course, we don't want to do this. It's computationally inefficient, and so it scales badly. And what you in most boostings is done is that we just approximate this Cation with the diagonal one. So we just keep only main diagonal of this matrix and set other values to 0 in order not to deal with the matrix inversion. Or otherwise, we can just forget about second order derivatives and just let's say take a second order derivatives that just in identity matrices. So yeah, at the end we will obtain the following solution. So this solution for the case when we have second order derivatives, but we just keep the main diagonal. And yeah, so actually this solution, it's analytical solution. We know we can solve this optimization problem. Okay, so then if we plug all these solutions back to our loss function, we'll obtain something like this. So we'll have just a constant -1/2 multiplied by sum of some functions which we compute at every leaf of our tree. And these functions, they're in our paper and in literature, they're called scoring functions. And these functions, they will play a central role later because we will deal with some approximation of these scoring functions. But yeah, so we'll get back to it later. So something we'll use later on. Okay. So we discussed how to, given a tree structure, how to compute optimal leaf values. And let's talk a bit about how we can actually find an optimal tree structure. Of course, it's a problem which is much more complicated. So in GBDTs, it's done in the following way. So we just, again, we use a greedy algorithm. So we start with single leaf. At each step, we want to add branches to our tree. We want to make a split. And to make a split, what we need to do, we need to iterate through all possible, through all leaves we have in our tree, through all possible features of our data set, and through all possible thresholds for each feature. And then for all these possible splits, what we need to do, we need to compute some of the scoring functions for R left and R right. So it's just our split. So our split is just is based on let's say feature J and on some threshold. So we'll obtain. So after split, we will have two more leaves, and we just need for each of so for each leaf, for each new leaf, there are only two. We need to compute sum of scoring functions at these values. And then, so our goal, so what we do, we choose the split which maximizes this sum. Why we do in this way? Because in a sense, so we want to minimize our loss function, and what we can do, we can compute what is called usually information gain. So we can compute the value of loss function before and after the split. And then if we consider the difference of these two, we will just obtain something like this, right? So all the terms, they are canceled, and we will just have -1/2, and then the scoring function at leaf R before the split, and minus S are left plus S are right. So this term is just a constant because it doesn't change from split to split. So and if we want to maximize information again, so this means that we need to maximize this. All right, so this is what we do. So we need to iterate through to make a split. We need to iterate through all possible leaves, features, thresholds, and to compute this sum of the scoring functions. And yeah, we choose the split which maximizes this sum. All right, so I think it's more or less clear that this step is the most computationally expensive because here again, we need to iterate through features, thresholds, and through all possible leaps. And this is only to make just one split. Yeah, you can consider this step as a bottleneck of GBDTs in general, no matter what algorithm you use, no matter what it is, GBDT, like GBM or CatBoost or GBoost. All right, so let's proceed. So what we actually did in our paper, you can, so like from previous slide, you saw that we need, during our split search, we need to compute the scoring function many times. And our idea was to make this step in a sense more computationally efficient. So since we are dealing with multi-output problems, so meaning that we have outputs which are multidimensional, our goal was to compress the data we have, not the data set, but the data we use in this computation of scoring function, so that it is not linear in D, which so D is just the dimension of our output, but sublinear in D. So yeah, this is like the main idea is to make so to make this iteration, huge iteration, faster. Let's compress data we have so that we waste less time on this step. Okay, so the idea was to do something with output dimensions, and of course we consider single tree LGBDT. So meaning that we construct just one tree, and each leaf has a response which is multidimensional. It's not a one-versal strategy. Okay, so if we consider once again the scoring function, and if we rewrite it in a different way, we can obtain something like this. So we'll have just a matrix which is multiplied by a vector. Then we need to compute just the Euclidean norm of this vector and divide by the number of elements. So the set cardinality, the number of elements in this leaf, plus lambda is just our regularization parameter. So the key point here is that this matrix G is just our gradient matrix, which has n rows and d columns. And so n rows we have, so our data set is of size n, so n is our data set size. We cannot do something about n, so we want to take into account all of the observations we have. But the number of columns is d, and so each column corresponds to an output. We have d outputs, and each column corresponds to an output. And in SketchBoost, and why it's called SketchBoost, it's due to the technique which is called sketching. What we do, we try to replace this matrix G, which is n times d, with another matrix. Let's say JK, which has the same number of rows n, but less number of columns k. So k is assumed to be much less than d. And we call this JK as a sketch matrix. Of course, in computational sciences, by sketching, people usually mean some like techniques which require some randomness, and not all of the methods where we consider they are random. They involve some randomness, but in any ways, I think it's a good name for a good name to use here, just like sketch matrix. All right, so our goal is to replace G with GK with a matrix with less number of columns, so that we don't lose too much information in a sense. So we want to we want these functions Sj and Sjk to be close to each other. So after like replacing full gradient matrix with its sketch, we want these functions to behave similar we want them to have similar values. All right, so we have in our paper like 4 main techniques, 4 main ideas, and of course I should say that we so the first comment is that there is no optimal solution to this approximation problem. So all of these ideas, techniques, we consider they're in a sense suboptimal. And the second is just so I want to mention that we considered many different other ideas, but these 4 seem to work more or less okay. So they work just the best out of many different strategies we used. Okay, so let's start with ideas. The first idea was pretty straightforward. So it's called truncated SVD. So we just replace matrix G, our gradient matrix, with its SVD version, truncated SVD version. And it works. So we have like a theoretical explanation why it works in a sense. So we're trying to solve an optimization problem, which is similar to approximate matrix multiplication. And we know that the best solution to this problem is SVD. So this was the first idea. But so even though truncated SVD works more or less okay, the main problem with this method is that it's computational complexity. So you probably know that if we want to compute SVD of matrix G, and if the size of matrix G is n times d squared, n times d, then the complexity of SVD would be quadratic in d, n times d squared. So here I assume that we have n which is greater than d. And so it makes the complexity not linear, but quadratic in D, which makes no sense. So we just increase complexity of our initial problem. Of course, in practice, it might work a bit faster than just simple GBDT. But again, so we wanted to have something like faster. And the second idea we tried, it somehow is similar to SVD, but it's let's say more straightforward one. So if we want to preserve the norm of the vector G times let's say V, then we can what we can do, we can just and if we want to reduce the number of columns in matrix G, what we can do, we can just throw out columns which correspond to the smallest Euclidean norm. So in our sketch, we can keep just k columns, which have the largest Euclidean norm. In a sense, this kind of is motivated by the fact that we want to preserve multiplication g times v, and we want to preserve norm, and it's more likely that values are going to be more or less the same if we keep the columns with the largest Euclidean norm. So this is the idea. Again, in the paper we have some more explanations, and even we have rates for this method. But yeah, the idea was the following. After top outputs, what worked also pretty well is random sampling. These two methods are pretty similar to each other, but in random sampling, what we do, so we don't choose the columns of matrix G, but we sample them with some probabilities. And again, so we computed the optimal probabilities in this problem, and it appeared that the optimal probabilities are just probabilities which are proportional to squared norms of columns of matrix G, of our gradient matrix. So we know this optimal probabilities, and yeah, so our sketch is just the following. We just sample rows, we just sample columns from matrix G, and we need to additionally normalize them, but it's just a small comment. So yeah, this was the idea. And the last method, the last idea I'm going to talk about is random projections. So we can think of random projections in the following way. So in random sampling, what we actually did, in a sense, we can consider random sampling as multiplication of matrix G by some other matrix pi. And in this matrix pi, we have almost all elements equal to 0, but in each column, we have only one in a random location. And this one in a random location actually just shows what column to keep in our sketch, GK. So we can proceed with this idea further and to consider like general matrices pi, which like instead of just one in a random location for each column, they have so they're just filled with random numbers, with random generated values. And that's it. So in a sense, this actually means that we, in GK, each column is going to be a weighted sum of columns of G. And again, so this idea, it goes back to random projections and their properties, to Johnson-Lindenstrauss lemma. And of course, we can have here like different possible distributions. We just picked the most simple one, but we had different experiments with other distributions, but they worked more or less the same. So yeah, random projections method, it means that we multiply matrix G with another matrix pi. And this matrix pi is just a matrix which is a random matrix filled with normal random variables which are centered. And so again, we have some normalization here, but so these are details. All right, so then I'll just let Anton speak about different about our implementations and about numerical experiments. But so what I want to say at the end is that all this idea I presented, so it's obvious in the sense that they're gonna reduce training time of GBDT. Because this was our initial idea, so we considered like different sketches, and of course, when we reduce the matrix size, so this gradient matrix in size, of course, we'll obtain just training times which are less. But at the same time, and I think it's like the main point of our paper, it wasn't so obvious how this will affect the performance, general performance of the model. So what we expected at the beginning is that performance will also, so it's will be like so. We'll obtain like more errors, and performance would be a bit worse. But yeah, so we'll see. Yeah, Anton will show you that it's not the case. And in a sense, so this was actually not obvious at all at the beginning. Okay, thank you so much. And Anton, you can continue.
Okay, thank you, Leonid. Let me share my presentation. Okay, I suppose everybody see.
Yes.
Okay, now we'll speak about the experimental part of our work. But first, let's discuss the implementation issues. What's the problem about experimenting with GBDTs? The problem is that modern gradient boosting toolkits are actually the black boxes written in low-level programming languages. So the result is very difficult to customize it because first you need to understand what's happened inside, and even though the idea of boosting is quite similar, but the implementation details of different frameworks are a little bit different. So the first you need deeply understand what's happened here. The second, of course, you should know the low-level programming language, which is not common for data science community. Yes, someone do, but you can expect it from every data scientist who has some idea about how to improve gradient boosting. So that's why sometimes you cannot easily implement some new ideas, yours or even some from different papers. And that's how we came to the idea to build our own gradient boosting toolkit. And here it is, we called it Pyboost. So a Pyboost is a gradient boosting library written on Python. So it's open source, and you can see it on the GitHub. And you can just look at our repository. You can also star us if you want, and or just install it using Pipey. So it's very easy to install. So what's special about this implementation? It's written in Python, as I said, and you can expect that it's gonna be a little bit slow, but actually it's quite fast. That's happened because Pyboost is written only for GPU, so it's no CPU implementation for Pyboost, and it uses Python GPU libraries like QPy and Number. So if we, for example, decide to build a CPU implementation, yeah, it's going to be much slower. But GPU implementation with comparison to state-of-art implementations doesn't lose too much time. Yeah, maybe for some common tasks like binary classification or regression task, we can lose a little bit speed, maybe somewhere 20% to the top performer, sometimes 50%. Yeah, it's a little bit slower than state of art, but it's still fast enough to perform our experiments. And we can make faster by introducing some new algorithms. Also, you can think about Pyboost like simplified a little bit gradient boosting toolkits. here we didn't consider any features that are not important to our research area. For example, we didn't care about category encoding. We implement only one grow policy. For example, CatBoost supports 3 growth policies, GBDT supports 2. For our research, it doesn't matter, so we implement only single grow policy, depth-wise, the most classic, like original XGBoost grow policy. But it supports all the main hyperparameters that you use to tune for any state-of-art algorithm, the most important ones. But what is good about this implementation? It's very easy to customize. For example, what you can do for XGBoost or CatBoost, you can maybe tune some parameters, write in a custom loss, but maybe it's over. Maybe you can control learning rate somehow, but it's quite limited space to control the training. For Pyboost, you can control almost everything. You can write your own row, column, sentence strategies. You can interrupt the train process on any stage. You can manipulate the data, the gradient, the Hessians, the build trees. And you can write some very crazy things with just few lines of code. And it's like native for Pyboost because, for example, if you decide to write your own loss function for, let's say, XGBoost, you will have some overheads. For example, you train your XGBoost on GPU. It's extremely fast at the time when tree is built. But after that, to compute a loss, it falls back to a Python mode. Data is moved to CPU memory, then your custom loss is computed, and then you copy it back to GPU memory. So it's a very big overhead. That's why it becomes not very efficient to write your custom losses, for example, for XGBoost. For CatBoost, for Pyboost, it's a little bit different because it's written on QPy mainly. So if you write your custom loss using QPy framework, there is no overhead. Everything happens on GPUs. No copies, no data transfers. So it's native. You can think like maybe you are not familiar with GPU programming, but the QPy is a very simple library. It's actually copy the NumPy interface, NumPy API, and implement all the operations which NumPy can do, but with GPU arrays. So you just write a simple code that you typically write for manipulate NumPy arrays, and just replace NP with CP. So it's very simple. And
Anton, there is a question in the chat. Does Pyboost support defining the custom loss function without defining its gradient and Hessian to rely on the autograd to calculate them?
It's like a feature that I want to implement in the future. For now, not. You should calculate the gradients and Hessians by yourself. But yeah, I'm thinking about this feature, and I think it's not very difficult to implement. Because, for example, if you consider a torch as an autograd framework, there is like, you can manipulate the QPy arrays and torch arrays without copying. So inside, they have the same CUDA array interface. So you can just refer to the same array like a torch tensor and the same way as a QPy array. So there is no copy and it should be quite easy. So yeah, I'm thinking about this, but for now, no.
Thank you.
Okay, so you can think like Pyboost. Now I'm explaining like a difference between Pyboost and SketchBoost. The SketchBoost is the particular algorithm that help you to train on the multi-output setup. But Pyboost is just a toolkit that will help you to build your custom strategies. And SketchBoost is implemented, is a part of a Pyboost library. And that's the difference. So SketchBoost is like a algorithm, theory. Pyboost, it's like a practice implementation. Okay, let's go now. Okay, let's speak about experimental results. To estimate how good is SketchBoost, we compare it with a set of baselines. The first and the most important baseline for us is comparing the SketchBoost with a pure Pyboost implementation. Because you can think like, if Pyboost implementation is not as good as XGBoost or CatBoost, the negative ways are the same for Pyboost and SketchBoost. Because they share the same engine inside. So the difference between SketchBoost and Pyboost is all the algorithm difference, what give us the sketching strategy. The second, of course, we're interested how fast we are comparing with XGBoost and CatBoost, so current state-of-art results. Sometimes we are asked why we didn't consider a light GBM as a baseline. For the moment, I'm not sure about how the situation is now, but for the moment 1 year ago, when the research was done, light GBM had very poor GPU implementation. So if you want to compare two GPU-based algorithm, the light GBM is going to be a loser, even comparing with Pyboost, because as they say, they didn't port all the algorithm to GPU, only the bottleneck. But Pyboost, XGBoost, and CatBoost are full GPUs. The second reason that they don't have a built-in multi-class or multitask regimes. The third, even though you can say about multi-class, for multi-class it shares the same strategy as XGBoost. So we consider XGBoost like a best representative or one versus all strategy, and the CatBoost for the moment is the best representative of fair multi-label, fair single tree strategy. And that's why we consider only two boostings into comparison. And the last baseline we take, it's a deep learning model. We took TabNet as an example because what's good about deep learning? If you have, for example, a big deep learning tabular data model, you can have like very heavy encoder part, and this heavy encoder part is not affected by the number of outputs. Only the head only the last linear layer is going to be affected by the number of outputs. So instead of gradient boosting, it scales very good. So maybe we should not solve our problem. If neural networks are the winner, why should we care about how boosting works? That's why we should take into account the deep learning baselines. Okay, let's discuss the experiment. The first picture is the similar experiment that we did on the synthetic data with 2 million instances and the different number of classes. And there is a train time for extra 100 iterations. And you can see the SketchBoost has much less time compared to other baselines. So you can even you cannot even notice sometimes the bars for SketchBoost. This is good news for us, but actually it doesn't matter that the full train time is going to be the same. Why? Because as I told before, all gradient boosting implementation has some constant costs, like costs for data transfer, costs for quantization. And the second reason is that sometimes maybe we can build very fast decision trees, but maybe these decision trees are too bad, so we need a lot of trees. So maybe in terms of speed per one tree, we are best, but maybe in terms of number of trees, we are worst. So it means nothing about the real world comparison. So let's go to the real world data sets. To make the experiments, we took some data sets from Kaggle, OpenML and Mulan repositories. We choose some data sets with different number of rows, features, and especially outputs. So we took data sets from 10 to even to almost 1,000 outputs. Here, this is just a subset. Totally, we had 10 data sets in our paper. So let's check the result about the speed. There is some plots. How can we understand that plots? Let's first look about the first row. There are multi-class data sets. All the comparison is made for GPU versus GPU implementations. In the first, we can notice here that SketchBoost is always faster than a Pyboost. That's good news for us. So algorithm really work if we don't take into account the implementation issues. The second good news for us that even though it's a Python implementation, SketchBoost still is a winner comparing with CatBoost and XGBoost. So sketching strategies are doing a good job, even comparing with low-level programming languages. For example, for 300 classes, you can see it's 40 times faster. So it's really high speed up. And then you can see that sketching strategies are faster even than a deep learning baseline. So maybe I should a little bit explain how the experiments was done. We train until the convergence. So for example, if SketchBoost needs more trees to converge, we give him more trees. So we use early stopping, and each boosting took the amount of iterations it needs. Okay, what about the down row? Here are the multi-label datasets. You should notice that the CatBoost times sometimes is very slow comparing to all the baselines. The reason of that is that CatBoost on that time, I don't know about how this situation is now, but for 1 year ago, CatBoost can train multi-label only for CPUs. So that's why implementation for CatBoost multi-label is not really fair. They are slow not because of the algorithm. It's just the difference for CPU versus GPU. But if you compare, for example, SketchBoost with XGBoost, that is GPU versus GPU, it's still very fast. And sometimes you can notice that speed up is very significant. Okay, and what about the accuracy? When we, actually it's quite obvious that we can train fast. As Leonid showed, we save a lot of computation and speed up is obvious. But we expect it's going to be like a trade-off between accuracy and speed. And we suppose like every time we should look for a good trade-off and so on. But actually, SketchBoost is the champion, even in terms of accuracy. For example, you can compare the SketchBoost with Pyboost. Again, SketchBoost always outperforms Pyboost. Moreover, often it outperforms even state-of-art implementations as the CatBoost and XGBoost. So sketching strategies not only help us to train fast, but it helps to make models more accurate. And again, we can check the tabnet. Tabnet is a loser here, comparing not only with the SketchBoost, but comparing with all the boosting family. So when we were thinking about how to explain these unexpected results, we can check the dependence of quality comparing to the number of dimensions that we used for Sketch. And sometimes we can see quite expected results. For example, the more dimensions we consider to Sketch, the better quality we have. But sometimes you can see that there is an optimal sketch size. So the bigger size not only make the computation longer, but even the quality is going to be less. So we explain this effect by the randomness that sketching strategists introduced to our training. So we add some diversity to the ensemble. That's why the models generalize better. So it's our assumption about the performance of SketchBoost. Even, for example, for Leonid's dataset, you can see the optimal sketch size equals 1. So the randomness here maybe is much more important, for example, than for more dataset, where we can see like expected pattern when more dimensions help to train. Okay. And here is like a bonus slide. When we published our paper on NeoRips last year, the same time there was a competition on Kaggle, and one team independently from us just took a gold medal just using our Pyboost. So they used like some deep learning models. They used Pyboost, and they say like Pyboost outperforms deep learning baselines, and seems to be a new state of art for multi-output, at least for this particular task. If you want to learn more, you can check the link. And I hope it's not the last competition. I hope Pyboost will show itself in future. Okay, to summarize, today we'll learn what is a SketchBoost algorithm, what is a Pyboost library, and how to use it in practice. So that's all we have to say you. And if you have some questions, we would be glad to answer.
Thank you very much for your talk. So colleagues, please don't hesitate to ask questions, comments, suggestions. Just a moment. So now you can unmute yourself and ask question by voice, or write it in the chat. It's up to you what's convenient for you. So any questions, comments, suggestions, welcome. So I see in the chat the comments that many thanks for the talk and for the library. And Daniel promises to try it in the product as soon as possible. So maybe.
Yeah, somebody already tried. Say it's like a good toolbox. Oh, I can, the last thing maybe I can mention here, the GBDT authors noticed this algorithm and they claim to implement it in near future for their multi-output strategies. So probably it's going to be very simple to use this sketch inside the GBDT. Probably it's going to be much more efficient than our Pyboost implementation, and we will be able to train even faster than now.
Do they announce how fast they plan to achieve it?
No, only like a future work.
Okay.
With no timing.
Okay. Okay. Okay, so maybe I'll ask some questions by myself. So
there is also a question from Oleg. Okay, it's about custom loss function.
We already answered.
Yeah.
During the talk.
Sorry.
Yeah.
Okay.
We asked it during the talk. Yeah. So can you please return to the?
Somebody wants to ask.
Nick, Nick, do you want to ask a question? Please don't hesitate.
Yeah. Firstly, thank you for this interesting talk. So I have a small question. So in that slide that you was introduced the sketch matrix that substituted the G matrix. how you estimate this k parameter that much less than d that you have the dimensional of answer, right? So yeah, what is the idea behind this? Do you just to try random substitution and yeah, try to estimate this from scratch from your data, or you have some idea how to find this k parameter?
Okay, a good question actually. Yeah, we had some idea about how to estimate the k adaptively from the data, but nothing about from our ideas work. This is bad news. So actually, the k is a hyperparameter. The good news that is that actually we can say that the algorithm is not highly sensitive of k. So you can think like maybe the difference between k equals 5 and k equals 10 could be very small. So probably to explain how to fine tune, I would recommend to do the following. You can just try k equal 1, then k, for example, equal 3, and k equal 10, and probably choose one of these. Because the intermediate values works about the same, and I didn't meet a task where when k more than 10 really helps.
So it means that your approach is fully empirically, right? You just from your from your experience, you have opinion that this number is okay for this parameter, right?
There are some plots here, and you can see the difference of quality depending on k. Yeah, we have some expert knowledge about how k should be set, but if you, for example, have no knowledge like we, you can just find its optimal value for that hyperparameter together with all that hyperparameters you typically fine tune for gradient boosting. For example, you are looking for call sample, subsample, you just put the k together with all these hyperparameters to one optimizer, for example, for TPE search, and find it as usual. If you want my recommendation about the grid values from 1 to 10, probably it's not going to be bigger than 10.
Okay. Yeah, I'm asking because it's remind me a bit that I listened from the Ivan Asilidis, I think, in his talk. He has some works about the low rank approximation of some tensors, matrix, and so on. So it seems somehow related, right? Or not?
Probably Leonid.
Because let's
absolutely.
Give me minutes. I will be more precise. So he was explaining that this is exactly related to the rank of the matrix. So it means that this number that you explain now, it's should be depends from the data really. It's not could be in the every case it should be 10 or 5. It mostly depends from the data, right?
Definitely.
Yeah.
Okay. Okay. Thank you, guys.
Thank you for question. Alexander wanted to ask a question.
Do you hear me?
In chat.
Hello?
Yeah.
Okay.
Yes, we hear you.
Yeah. Sorry. I found the link to your paper, so I can everything find there. Thank you. No questions.
Okay.
Question. So, what's your plans for the future? So, what if it's not a secret? So, what we should expect and some.
I don't think you should expect some plans about multi-output support. There are some features that Pyboost support for multi-output, except the sketching strategies. For example, Pyboost is a little bit more flexible for multi-output strategies. For example, today we discussed two main baseline, like a one versus all for multi-label and single tree for multi-label. But actually, you can imagine an intermediate strategy when you, for example, build for 100 classes classification task, you build 5 trees at each iteration with random grouping of outputs. So this feature is available. You can check it. And some people say it helps for their tasks. And it was a plan for our research, but we just implemented this feature without researching it from the scientific point. Another feature you could expect from Pyboost is support of multi-GPU training, of distributed training. We're working about this topic now. And maybe the last thing is going to be important, maybe, is support of causal models like uplift modeling and so on. We will introduce some algorithms for uplift modeling. The other features that we want to done, one is about autograd, and some maybe small changes. Don't expect anything else. Because it's not like a toolbox for which we have a lot of plans. We just want to have a toolbox for the case if we have some idea, we want to implement it fast. So if we have idea, we do. If we don't, just it waited time.
Okay, thank you very much. Colleagues, any other questions, suggestions, whatever, comments? Okay, maybe no questions. So again, great thanks to Leonid and Anton. And we wish you success in your, it's a very, I think, great product, Pyboost. We already tried it and it's quite successful in some Kaggle competitions. So thank you very much again. And then let's close this meeting. Video record will be on YouTube, I hope, maybe today evening or tomorrow. So good evening, everybody.
Thank